Okay, thank you very much, John, and thank you everyone for coming. And today I'd like to talk to you about the work I did during my PhD, namely the long-time evolution of accretion-induced collapse of white dwarfs to neutron stars. So before I start about the specific topic, let me give you a brief introduction on what we're talking about. So if we think about the stellar explosions that we're thinking in the 70s or 80s, the main idea that we had is that a massive star would do a core collapse supernova explosion, and then we would categorize them based on the spectra. So the rough idea was that if we had a hydrogen in the spectra, then this would be a massive star collapsing and forming a neutron star or a black hole. But if we don't have hydrogen, then that probably means we have a star that doesn't have any hydrogen envelope, and probably it's also a white dwarf. Then with improving instrumentation and better spectra, we kept finding more and more categories. And then the idea is that based on the different lines that we see in the spectra, we have different supernova. However, now the picture is a bit more complicated. So when we talk about stellar explosions, then we don't talk only about supernova, but we have many more categories of supernova, such as the superluminous supernova. We recently observed a kilonova and a combination of we had the gravitational wave emission and an electromagnetic emission at the same time, and this was the first signature of two neutron stars merging and producing a gravitational wave and electromagnetic signature. And also what we found there, and that was very important, is that from the spectra we identified the heavy element of strontium, which makes neutron star mergers a side of our process nucleosynthesis, which means that it's a procedure which means rapid neutron capture that basically creates heavy elements. So all this zoo, if you like, of stellar explosions or transients can give us a very significant information about the life of stars, how they end their lives, and also how they enrich the galaxy with heavy elements. So my topic specifically is the accretion-induced collapse of white dwarfs to neutron stars. So we're talking about white dwarfs that they collapse and they form neutron stars. And you would wonder where it is in this diagram. So you have basically the luminosity as a function of the time scale. And the answer is that we don't know because we haven't observed that yet. However, it's a theoretically motivated scenario. We think it exists in nature, but for various reasons, for example, it's very faint. We haven't observed it yet, and probably will be located somewhere here. It's probably a bit fainter than type 1a or kilonovae. So let's move now to the topic of this talk, which is the long-time evolution of accretion-induced collapse of white dwarfs to neutron stars. And I will start from the end, so from neutron stars. As you all know, neutron stars are very compact objects, very heavy. They have the mass of the sun, but the size of a town. And when we think about neutron stars, the first thing that comes to mind is that they are born in a core collapse supernova event, which is a massive star that has burned its elements and has moved through all the stages of stellar evolution, has developed an iron core that eventually it collapses and it can form either a neutron star or a black hole. Or additionally, which I think I do put here, also electron capture supernova can form neutron stars. Another way to form neutron stars is via neutron star mergers. In the majority of neutron star mergers, we will form a black hole. However, there are also some neutron star mergers that they are stable enough and they can create a very heavy, long-lasting neutron star. And there's a third alternative scenario, which is the collapse of white dwarfs. And basically, we're talking about heavy white dwarfs that are mainly composed of oxygen, neon, and magnesium. So these are very important in general in the universe because, as I said, they are sites of heavy element and nucleosynthesis. They emit gravitational waves, and they can set constraints for the nuclear equation of state. And in my work, I focus on the neutron star formation of the particular case of white dwarfs collapsing to form neutron stars. So my main work and what I will be talking to you today is what are these accretion-induced collapse, why they're important, the significance of our work, and moving on the results, the AIC, accretion-induced collapse in short, AIC dynamics, what kind of neutron stars we form from AICs, and also the ejecta properties and possible observational implications. So let's start thinking about a white dwarf that is the end stage of stellar evolution for low mass stars. And for low mass, I mean stars less than 8 solar masses. These stars, they develop a degenerate core in their centers, and in many cases, they end their lives as a white dwarf. So many white dwarfs, they are not alone in the universe, but they belong in binary systems. So we have two different cases. The first case is that we have a companion star that can be a red giant or another main sequence star and a white dwarf, or we can have a white dwarf in a binary system orbiting one each other. And then what happens is that their orbit shrinks between the two white dwarfs, or we can have accretion from the companion star or onto the white dwarf. This is usually the scenario that makes a type 1a supernova, which is a thermonuclear explosion of white dwarfs. However, there is another scenario that basically is the white dwarf collapse. And when the white dwarf collapses, it produces a neutron star, which is accompanied by a neutrino-driven outflow. And that's what we are calling accretion-induced collapse. Let me now go into more details on how does this work. So we want to have a heavy white dwarf that consists of oxygen, neon, magnesium, and has very high central densities. In my work, I don't ask the question how we end up to have this white dwarf. There are different scenarios, and they depend on a lot of properties on the accretion and on the kind of system or the kind of progenitor system that we have. But in my work, I basically have studied the evolution of this object from here and onwards. So I assume that I have a white dwarf that for one reason or another has very high densities in the center, and also its composition is mainly oxygen and neon. So what happens is that due to electron capture, we lose the degenerate pressure support, and then this starts to collapse. As the white dwarf collapses, in the center, we will reach nuclear saturation densities, and then we cannot compress the matter anymore. And then what happens is what we call a core bounce, that basically the matter, it's like hitting water onto the wall. Okay, not water, but hitting a mass onto the wall, and then it will bounce back and create a shock wave. And then in the center, we have a very hot proto-neutron star that emits a huge flux of neutrinos. A small fraction of these neutrinos will be reabsorbed in the still collapsing matter of the white dwarf. And then as the neutrinos are absorbed in this material, it will hit the material and it will accelerate the mass outflow. So we end up having a proto-neutron star that will cool down and become a neutron star. We have mass ejecta that is driven by neutrino heating. And in case of rotation, and we assume that we will have rotation due to the mass accretion and angular momentum from the progenitor system, we create a disk around the neutron star. So the important questions to ask here is the ejecta composition and mass. What are the properties of this this outflow that is created from this kind of objects, and also what kind of neutron stars we create in these objects, from these objects. I hope I convinced you so far that the accretion-induced collapse is an alternative scenario for neutron star formation, is another site for heavy element nucleosynthesis, and there's been a long debate on whether it is an arc process nucleosynthesis, so a rapid neutron capture nucleosynthesis, and how much does it what's the percentage of AICs in the as an arc process side, and also it emits gravitational waves. So far, there are very limited models in the literature, and most of them, they treat the problem in 1 or 2 dimensions. And here I talk about numerical simulations of these objects. And only recently, the problem has been addressed in 3D. But one very strong caveat of the previous models is that they only follow the evolution of this object less than 1 second. And as I will show you, it is important to follow the evolution for longer times in order to capture the full ejecta properties. And here I want to give you an example of a relatively recent observation. We have this transient, the AT 2018 KZR, and here you can see the observations compared to some other supernova. This is after 1.9 days, 2.8, 3.8, and basically trying to do some Gilander, Sim, and Smart try to do some spectroscopic analysis of this object in order to identify which kind of object produced this this light curves and spectra. And they basically rejected the accretion-induced collapse scenario with the main motivation that the composition of the ejecta found in these observations do not match with the composition that is predicted in the literature. I will come back to this point towards the end of my talk because there might be some tension to this result. So coming to the goal of my work. So the aim of these numerical simulations and this work is to bridge the gap between the current modeling and observations. And to do that, we need to follow the long time evolution. And when I mean long time, I mean less than 10 seconds. It's very short, but the time scales are such that even if we evolve the system for 7 seconds, it's enough to capture all the relevant physics. And as I mentioned already, we simulate the post-merger or post-accretion configurations for a set of models. So we don't ask the question, what happens before? What happens to the white dwarf before it collapses? We assume that we have models that are ready to collapse and ask the question, what will happen after the beginning of the electron captures? And to do that, we use numerical tools. So we have radiation and hydro code, and very briefly, it includes gravity. It's also the Poisson equation, and we have some corrections for GR. So basically, we take an effective, an additional effective potential for that. We treat the stellar matter with grid-based hydrodynamics. Neutrinos are very important for these problems and cannot be ignored. They follow the Boltzmann equation, and the treatment that we follow is a 2-moment scheme, which basically means that we evolve the first 2 moments of the Boltzmann equation in order to describe neutrinos. And also we have a nuclear equation of state for a high density matter. So let me now briefly describe the progenitor models that we have. So we have 6 different models. One that doesn't have rotation and the rest of them, they rotate. So what you see here is that the Z X plane and color coded by the density. And here are the parameters of the models, but you don't need to focus to all the different numbers. The important thing is basically that we have a lot of different masses. So we go from 1.4 almost to 2 solar masses. And Y2 is above centrosecular mass, of course, but it rotates a lot. So we have, for example, this very heavy model, it has a large budget of angular momentum, so it can accumulate that much mass. And the motivation behind these models is that we have basically the degenerate matter in rotational equilibrium with densities high enough to allow for electron captures.
Can I ask you a naive question?
Yeah, sure.
These are white dwarf masses.
Yes.
Most of them exceed the centrosecular limit. So
yes, just because when they rotate, when we include rotation, so
then you're going to exceed.
Yes, exactly. So this one, for example, it has a very large angular momentum budget. Yeah, so basically we only have this model that it doesn't rotate, and then the rest of them they rotate. And these rates of rotation in terms of 5 to 20 rad per seconds, they are it's considered a very fast rotation compared to stellar rotational rates. Okay. So they rotate very fast. The rotational laws, they come from an old work that they just assume accretion onto white dwarfs, and then the angular momentum transport basically results in this kind of rotational profile. But we take this as it is. A colleague of mine created this object based on all these assumptions, and then sure.
A question. So how do you get the nuclear energy production? Is there any nucleosynthesis?
So the code evolves the total energy, and then we have the part of, well, actually we assume nuclear statistical equilibrium in this. We have very high temperatures. And then actually when we go to temperatures lower than nuclear statistical equilibrium, then we just freeze out the composition. But we don't, in this code, we basically have only neutrons, protons, alphas, and the representative heavy nuclei. So we don't, we cannot treat individual nuclei.
But the initial composition that plays a role for the energy production of the nuclear statistical.
Yes, but in the initial conditions are already in this. We assume equal amount of protons and neutrons and very high temperatures. So everything before
you take the electron fraction basically.
Yes, that's it. Yeah.
Thanks.
You're welcome. Yes, and here you can just see the rotation as a function of a radius. We have very different rotational profiles that are again based on this law that I just described. Okay, so let's take now the upper left model, this one. This has a mass of 1.4 solar masses, and it doesn't rotate. And let's see what happens and how it explodes. Okay, so what you can see here is basically, again, the ZX plane of the model. And this panel shows the radial velocity, and this panel shows the density. This is at 100 milliseconds after core bounds, as we say. So basically, this model has collapsed, this white dwarf has collapsed, and then we have already created an outflow that propagates outwards. So here you can see a short convective motions that happens due to the negative energy and entropy gradient in the center. And then if we move on, so now we have the same figure at 1 second and at 6.7 seconds, but notice that the spatial scale has expanded. So this model doesn't have any rotation, which makes it to create an outflow that is spherically symmetric. So what you can see here is that the outer parts of the white dwarf, they just expand. This is very little mass here. And then as time goes by, we have a neutron star in the very center. I mean, it's not visible here because the scale is very large. And then the ejecta have detached from the central object, and they just propagate outwards in almost in a homologous scale. And what is important to understand is what are the conditions of this ejected material. So now we have the same plot but different quantities. So here we have YE, which is the electron fraction. I'm gonna talk about it a lot during my talk. So orange means low YE, which means neutron-rich material. And then the more purple is proton-rich material. And then on the right-hand side, we have the entropy. So what happens in the beginning is that due to electron captures, we create neutron-rich material. This is again at 100 milliseconds after core bounce. And as we continue to evolve this model, this material propagates outwards and also first. So if we would observe this, initially we would see first this material here, which is neutron rich, but at later times, so you see the inner part is proton rich, so it has different composition. So, and you can also see that also it's almost at 7 seconds, the pattern stays the same. The proton-neutron star has cooled. It doesn't alter the conditions in the outflow anymore. And that's why it's important to follow the evolution until late times. And let me now show you how this looks in the mass YE diagram. So here you can see the ejecta composition. So what we have is the mass, and the mass is of this material here. That is the ejecta from the white dwarf. Basically, the white dwarf has collapsed. It created the neutron star in the center, and then very little material is ejected outwards because of this neutrino heating that I was talking about earlier. And we want to know what are the conditions in this ejected material, because this is important for the kind of nucleosynthesis and the kind of light curve that we would observe or measure in this kind of phenomenon. So here again we have the mass of this ejected material, and this is the electron fraction. Electron fraction means that if we are in this regime, so less than 0.5, this is neutron-rich material. So this is the material that would do our process, and then we have proton-rich material. The neutron-rich material basically comes first, so the different colors also show the ejection times, and just notice that this very, very light blue or purple here is the initial ejecta, and this is neutron-rich if we don't include rotation. Spoiler alert. And then at late time, so you go the very dark blue, this small parts here, this goes to the more proton-rich regime, which is basically this material here that comes from electron-neutrino absorption, and only comes at later times. Let's now see how this changes if we include rotation. And I will show you exactly the same figures, but for rotation. This is a heavy model that rotates very, very fast. You see at 800 milliseconds, again, we have radial velocity and density, how asymmetrically it creates this outflow, which also keeps its shape at 1 second and 6.2 seconds. So basically we have a polar outflow, because at the poles we don't have any rotational equilibrium, any rotational support, so the material can fly out. And then we also create some material here in white. This is not ejected. There is a material that stays in rotational equilibrium around the proton-neutron star. And so what you see here is how different the shape of the outflow looks like, which you could think, okay, why do we care? We care because this material, we have to think how this material is exposed to this neutrino flux in order to identify what kind of composition it will have. And let me show you a video how it explodes, so you can see it also. So this is the density, radial velocity, YE, electron fraction, and entropy. And then you see the collapse, how it collapsed, and then basically the outflow is driven through the poles. Here we have, so this dark color shows proton-rich material. I will explain that in a while. And then here in the center, so what is basically density above 10 to the 11, we assume this is a neutron star. And then there is a lot of material. So all of this material stays in rotational equilibrium outside of the proton-neutron star. And now, I don't think you can see that, but this is almost at 1 second. So we have proton-rich material from the poles. And here in the very light yellow, we go towards neutron star, and I will explain that in a second. So what you see here is, again, I show you exactly the same figures at the same times. And here we have, again, YE and entropy. So what you can see here is basically two main points. The first one is that at the poles, we have the proton-rich material, which is purple. And then at the mid-latitudes, we get this neutron-rich material, which again can have an impact on the nucleosynthesis. And also, as we go at later times, we get more neutron-rich material. That's why it's important to follow the evolution of these objects for late times. And then if I compare this to what has been already done, usually people stop here, and then that's the composition that they think it's final. But it's not final, because as the proton-neutron star cools, it can still eject some material at later times. And when I mean later, later than 2 seconds, for example. So if we include rotation, everything is, the picture changes. The outflow is very different, and the properties of the ejected material is different. And let me show you now also how it looks in this diagram I showed you before. So again, we have the mass as a function of the YE. And again, for low YE, so less than 0.5, we have neutron-rich material, and YE above 0.5, we have proton-rich material. And what you can see here is that this patch here comes from the initial ejecta, which means less than 200 milliseconds. So the initial ejecta is proton-rich, and only after 2 seconds, we get this material here that is neutron-rich. And I will show you directly how this compares to the non-rotating model. So this is the rotating model, and this is the non-rotating model. So if we don't include rotation, initially the ejecta is neutron-rich, which comes from electron captures, and this is very similar to electron capture supernova ejecta composition. If we include rotation, the initial ejecta is proton-rich, and only at late times we find low YEs that they could potentially explain some kind of R process nucleosynthesis. And let me now explain you why this happens. As I mentioned before, what sets this electron fraction, the YE, is the neutrinos. So what you see here is the luminosity of the neutrinos as a function of time. And this is the non-rotating model, and this is the rotating model. The different lines are different species of neutrinos. So in our numerical simulations, we evolve the electron neutrinos, electron antineutrinos, and the representative heavy lepton neutrino species. And then the important thing is that the black lines are, I calculate the luminosity at the poles. The blue is at the mid-latitudes, let's say 45 degrees or 50, and the red is at the equator. And in the non-rotating model, you don't see any difference because it's spherically symmetric, which means that the neutrino flux is spherically symmetric and there's no difference. But if we include rotation, at the poles, we have much higher neutrino luminosities for all the species compared to the rest of the directions.
So why is this physically?
Yes, I will explain this at the moment. So what you see here is basically, okay, we have the upper left panel is density, YE, which is the electron fraction. This is the number density of electron neutrinos, and this is the ratio between anti-electron neutrinos and electron neutrinos. And the lines, it means that it's a region that we identify as neutrinosphere, which basically means that inside here, the neutrinos, basically, they cannot, they are trapped and they don't diffuse outwards. And then when we have a spherically symmetric model, then we don't have any angular variation of that. But here you can see how different the shape of these neutrino spheres. This is for electron neutrinos, and this is for electron antineutrinos. And then we have two effects. The first effect is that at the poles, the neutrino sphere is basically we have more regions. So the material here is exposed to a higher flux of neutrinos compared to the equator and the mid latitudes. And the other one is that basically the electron neutrinos and electron antineutrinos spheres, the radii are very similar, are very close by the poles compared to the equator. So basically that means that electron neutrino absorption here is favored because when the neutrinos are streaming from the same region, they basically have similar temperature and similar energies, which makes their rates similar. But when the electron antineutrinos, they come from a deeper part of the protoneutron star, then they come from a hotter region and their mean energies are higher. So these two effects, they result in this reaction. So we have electron neutrino absorption in this material here. It's favorable, and that's why we create the proton-rich material at the poles, and only the neutron-rich material in this direction over here. And then at the equator, the material is in equilibrium, so we cannot eject it in my simulations. Because basically what happens here is that, so we have created the neutron star, and then the disk stays in rotational equilibrium. And in order to treat properly numerically the disk, we need some kind of either viscosity or magnetic fields to allow for accretion and the distribution of angular momentum. And here I just show you the total ejecta composition for all our models. So each one of the lines, they just show you different models. Again, neutron-rich material, low YEs and high YEs means proton-rich material. And what is important to notice here is the following. The total ejecta masses of this kind of objects is in the order of 10 to the minus 2 solar masses. So we're talking for very little mass ejecta. And also, the ejecta distribution is very different. So if you compare the black line, which is the non-rotating model, with the ones that they rotate, and actually going in this direction in the colors, we have more and more angular momentum. We get a very different composition of the ejecta, which means that the nuclei that will be synthesized there, they will be different. And I was telling you about our process nucleosynthesis, which is the rapid neutron capture. And here, this is just an example of our process material, the abundances in our solar system. And basically, when we have, that's why the YE is very important. So the YE is one of the parameters that is very, very significant to set what kind of nucleosynthesis that we have. And there's been a lot of debate whether AICs will make our process or not. So in most of our models, we don't go to very low YEs. So basically, if we have YE of around 0.2, we can say that, okay, this is an R process side. But also, so here, this is just a rough estimation of what kind of elements they will be synthesized compared to the YE. So most of our material is actually in this region here. So we have YE more than 0.25. So the majority of the ejecta will not make strong R process nucleosynthesis, which would be this region here. And I also want to compare with some previous works. One previous work, because that's only existent. But so, okay, this is again the mass ejecta as a function of the YE that I showed you before. This is a rotating model that we get this neutron-rich material only at late times. And this is the same plot, two different models. This is non-rotating, or actually very slow rotating, and this is fast rotating. So the model that I'm showing you here, it would correspond to the solid line, again as a function of electron fraction. So what you can see comparing these two plots is that in their work, most of the ejecta comes with YE less than 0.35. When the majority of the ejecta is at this low YEs, then we can say, without calculating any nucleosynthesis at the moment, that this will be dominated by our process nuclei. While in our work, most of the ejecta mass comes basically from the with YE higher than 0.35, which is just a rough estimate to distinguish between the different regions. So it will not be dominated by our process, which means that only in very specific conditions we can synthesize a strong R process. And now I want to remind you about this transient that I showed you in the beginning, that they basically discarded the possibility of an accretion-induced collapse, mainly because the composition that they found doesn't agree with the composition that is suggested in the literature, which is so far that AICs will do our process. Of course, we haven't done in our work the detailed nucleosynthesis analysis, but there is an indication that will not be dominant by our process. And now slowly moving to a slightly different topic, and I'm close to the end. I just wanted to show you what kind of neutron stars we form in this kind of phenomena. So here you can just see a zoom in and the cross-sectional cut that shows different quantities. So we have density, radial velocity, entropy, and electron fraction. This is a fast rotating model. And what is above 10 to the 11? Here we have a very oblique neutron star. We have a lot of material that stays in rotational equilibrium, but unfortunately we cannot treat it at the moment. And there is a large variation in the entropy and electron fraction. So here we have proton-rich material in the poles, and then neutron-rich material in the mid-latitudes. So what we find is that we form a neutron star that varies in mass. I just would take these masses with a grain of salt because we still have the disk that it partially will accrete onto the neutron star. So from almost 1 solar mass to 1.4 solar masses are the neutron stars. They are very oblique and they rotate very fast. So we also find basically millisecond rotating neutron star in these objects. There's a lot of mass that stays in the disk, and the mass ejecta is in the order between 10 to the minus 3 to 10 to the minus 2 solar masses, and it varies a lot from model to model. And the main parameter, the main condition that defines how much mass will go in the disk in the ejecta is the initial angular momentum profile of the initial system. That's why it's very important to basically have more realistic models for the initial conditions. So when we have very high angular momentum in the beginning, a lot of mass will stay in rotational equilibrium. And for example, this model over here, the last one, and then we will have very little mass ejecta. And then when we have not slow rotation, but lower angular momentum, then a lot of the mass can be ejected because less material can stay in rotational equilibrium around the neutron star. And this can be directly reflected in the explosion energies. Explosion, a lot of quotations, because this is a neutrino-driven outflow, not compared to any explosion as we talk in type 1a supernova or quark collapse supernova. So basically, this is the total energy of the mass that is ejected for all the different models. So the different colors, they correspond to different model. And the important thing here is that we find explosion energies in the order of 10 to the 10 ergs, which is one order of magnitude less than the typical core collapse or type 1a energy. And there is a very large spread in the energy. So we cannot talk about any canonical explosion energy here. And I just want to point out two extreme examples. So this one is the gray line, this model, the one on top, which has the highest ejecta mass and the highest explosion energy. And why is that? It's because it has low total angular momentum in the beginning, which means that there is very little material staying in rotational equilibrium around the neutron star, and which translates to that, okay, we can allow more material to be ejected with a neutrino-driven outflow. And then the other extreme is this model that is very heavy and has very high angular momentum, which is the one here, that basically has 10 to the 49 ergs of outflow energy. This is because there is very little mass ejecta, and because most of the mass stays in disk. This is, though, a very particular model because it has such a high angular momentum that while it collapses, it doesn't reach, it doesn't do the typical, actually, it doesn't reach nuclear saturation in the center. So there's a lot of matter that this is something that we call centrifugal bounce, which means that the material is not compressed to the maximum as in if we don't include rotation. So this is a very particular case that, in my opinion, it needs more physics to understand and how it will explode. But the main message is here is that we have low explosion energies and a very large spread to the energies. So that brings me already to my summary and conclusions. I hope I convinced you so far that neutron stars can be formed from collapsing white dwarfs. This is the accretion-induced collapse scenario for neutron star formation, and I have tackled the problem of the long-time evolution of this accretion-induced collapse for a representative set of progenitor models. All the models show that they have neutrino-driven outflows. The outflows are very low in energy and low ejecta mass if we compare it to a core collapse or a type 1a supernova, for example. We find very fast rotating neutron stars that are surrounded by disks, and the ejecta are very asymmetric in their shape and properties due to rotation, which can have an impact for nucleosynthesis. So our models can now be used for detailed nucleosynthesis calculations, which is not included on this work, and also light curve modeling, and hopefully at some point we will observe it. Thank you very much, and have a question.
So thank you very much, Eirini. Are there any questions also from the
online people? Any questions?
Before, can I ask?
Sure, yeah, go ahead.
So you accrete the matter, and the matter is put on a white dwarf in a uniform way, spherical symmetric way, or
in my work, I don't address this question. So if I just show you the models that we use,
yes.
Basically these are models ready to collapse. So we don't assume any accretion, or they're made to do this accretion-induced collapse. The question, what happens before, is very interesting question. I'm very interested in that, but we cannot address it in this with this kind of numerical treatment.
Okay.
But basically, there are some assumptions that they come into the construction of this white dwarf, which is, for example, the mass accretion rate is around 10 to the -7 solar masses per year. And I think and also we actually assume a simple equation of state to construct this model. The reality is very different, because when we accrete some mass, some kind of nuclear burning will take place. But this cannot be addressed with these numerical tools that we have here. here we just have models that they are ready to collapse, and we just calculate what happens afterwards.
And a second question with the neutrino anisotropy, or the neutrino emission anisotropy. Is this due to optical depth effects? That is, neutrinos can escape more easily
Yes,
in the polar direction?
yes, but this is due to rotation. So rotation introduces this
Yes.
this shape. So basically, what is when we don't have rotation, everything is spherically symmetric. The conditions, density and temperature are spherically symmetric along all the directions. But here, the conditions of neutrinos emitted in this direction are different compared to the neutrinos emitted in this direction. So the point at which matter becomes optically thin for neutrinos.
Conditions themselves. Is it denser material
Yes.
this way, and
Here.
therefore it's easier for the neutrinos to go up that way?
Basically, what happens is that because of rotation, we get this oblique shape. So we have similar density here and here, but these are two different points, and they have. Okay, so here the electron neutrinos and electron antineutrinos, they stream off from a region with similar conditions, while here the electron antineutrinos are streamed from this region here, and the electron neutrinos from this region. And these two regions, they have different densities and different temperatures. So their respective absorption rates will be different. But this is an effect of rotation. Only because of rotation, we get this oblique material, yeah.
So
Maybe a naive question. So if I understood that correctly, depending on whether you consider rotation or not, there is transition from proton-rich material to neutron-rich material. So my question is there a time window during this evolution where you could have nucleosynthesis from P process or RP process instead of plain?
That's a good question. I have to admit I'm not an expert in nucleosynthesis, so I think I don't remember the exact conditions for different kind of processes, but basically for that neutron-rich material, it's very easy to have R process. What's S process you said, or
P process
P
or
process.
rapid proton? Because there is a proton-rich material.
Yeah.
High temperatures.
Well, proton rate is 0.5, so it's normal nuclear matter. It's not like super proton. It's symmetric.
I'm not exactly sure what's the YE to get.
You would need like electron fractions of like close to 1.
Okay, no, this we don't get.
P process, you need the
For P process.
for P process.
Thank you for this very interesting. One question is, so this is for models for accretion-induced collapse, where you have a degenerate oxygen magnesium core. In the electron capture supernova, you have this common thing that again, you have a degenerate core, oxygen magnesium, but physically it's different. That in one case you have Riemann from a companion, in the other
But
case,
the core is the same.
but the core is, so my question is, what would be the differences in your models if you wanted to say I model one kind of phenomena compared to the other kind of phenomena? Or would you expect that, can you say that these models in principle can address also electron capture supernova cases, or that some of them are not applicable maybe for electron?
Numerically, the treatment is the same, because you basically need to have we treat all these problems numerically. So what you need is to address neutrinos and high density equation of state. When you have an electron capture supernova, you have an envelope. So these are naked oxygen cores. So you have an artificial medium just because you have to solve the hydrodynamics. The other one is the whole star basically. So differences in terms, I mean, you need different initial conditions. So the starting point is different. The tools are the same, and also what I showed you about the. So this is, for example, the mass ejecta for the spherically symmetric, non-rotating model, and the composition looks very similar to electron capsule supernova. And the other thing is that, but okay, the mass ejecta is it's lower, I think, and also I think an electron the rotational rates are not as high. Just coming from stellar evolution, I think you cannot spin up so much the core. So I think these rotational rates are extreme for non-degenerate or not for stars, I think. Yeah.
So, but maybe to follow up on the question, so what is the influence of the initial temperature on the outcome of the models? Because that will also be a difference between electron capsules and accretion-induced collapse. As you have a very hot
Yes.
in one case, and in the other case you have like a cooler one.
Yes, that's true.
About the I mean, you already showed some models with different temperatures.
But I tell you why this comes from the they have different temperatures because they have different central. So we account for two different central densities, but this is again a question of would it really collapse? I mean, you know that better that in these conditions, maybe electron capture is not as efficient as oxygen burning, for example, but it is so. If we vary the initial temperature and density, the conditions are different in the center, and then in combination to rotation. So this is the model that I was talking about before that does the centrifugal bounds. So basically, we don't reach nuclear saturation densities in the center. So what we create some matter that is very dense in the center to call it a neutron star. But what will happen in reality if we treat the angular momentum transport differently, then I don't know what will happen to this model. It's very tricky because if you don't have that dense material in the center, then that affects the neutrino fluxes and energies as well, which affects the rates of electron neutrino and electron antineutrino absorption, which subsequently sets the electron fraction in the technically, this model doesn't create a shock wave. The only outflow that we see is from the neutrino-driven wind that comes after maybe 100 or 200 milliseconds. So it's the collapse dynamics is very different.
Sure. Okay, but
maybe I lost the point of the question.
I think so. If I look at the first two lines, you
Yeah.
have a model with a central temperature of similar central densities. Oh no, actually they're very different. So yeah. So I was wondering what's the difference between the first two models. I mean, even if both the central density and the central temperature are different. I mean, the first one could be closer to what as an electron capsule supernova core, whereas the second would be closer to like an old white hole. So the outcome very different.
Okay. Yes, because it's a bit hard to ask this question because this is not the only parameter that is changed.
All things change.
So what is more important is the rotation, because the initial central density and temperature. So I'm just saying that because we don't ask the question before. So our models will do electron capsules. They will collapse because of the equation of state, basically, of our model. these two models, they are constructed to have the same mass and to allow for the same mass. There's just a bit of rotation in the outer parts of the white dwarf. The central conditions, they impact the neutrino properties. So if we don't reach very high central densities, then the neutrino luminosities are lower for a less dense core. And then if we have lower neutrino luminosities, then this changes. I mean, again, it always compares, you have to compare electron neutrinos and electron antineutrinos. So the central conditions, they have effect in the YE, basically in the ejecta properties. But what is dominant is the dynamics here. How is the shape of this central object, and where and how much the ejecta, the outflow is basically exposed to this neutrino radiation.
Okay, thanks.
Yeah.
Maybe do you have any information on the energy distribution of the neutrinos and how they in the two different cases?
Let me see. I have the mean energy. I think I don't have it here, or do I? No. I haven't done any spectra or something like this, if you ask. But basically, when you have higher rotation, you have more mass stabilized in the center, and you don't create as dense cores, which translates to lower mean energies of the neutrinos.
You said that there's no shock in the same stuff, right?
There is this model. This model that does this this bump here at very low YEs. This has such low neutrino luminosities that it's not enough to create a shock wave as the let's say to accelerate the shock wave. So there's so much mass in rotational equilibrium that barely it starts collapsing, but then the rotation is so strong that it doesn't. The core is not as dense, so you don't have the typical pressure bounds that we see in core collapse supernova. So we don't reach nuclear saturation densities. It bounces because of rotation, because you have some material that cannot be collapsed more, and then as neutrinos, they basically get emitted later, then they can drive some outflow, but very, very little outflow, mass-wise. Yeah.
I have one more question, but maybe there is one question.
Oh, that was me asking.
Okay, so my question is, in some of your rotating models, you have a significant amount of mass in after a few seconds of Accretion-Induced. I understand that you cannot go further, and you're saying these are in equilibrium, rotational equilibrium. But like in a longer time scale, what do we have an idea of where this mass is going to end up? Do we expect it to fall back to the neutral star, change its mass, maybe I don't know, go extreme high, or do we expect it to diffuse pretty much?
Both. Yeah. There is a study from Metzger 2009 that they basically did the viscous evolution, taking some initial models of similar work, and what they find is that there will be some extra outflow. So what you expect if you treat this correctly is a part of the mass will be accreted onto the neutral star, and that's why I told you these masses that I have here. I mean, probably less than one solar mass. Probably that's not even realistic. And some of the mass will be driven outwards due to the neutrino-driven winds still. But then, if you go to even longer time scales, then the disk will I don't remember exactly, but it will basically dissolve because there's some kind of heating that will eject some extra material. So this mass will be distributed between the two. But then exactly how much mass you have to calculate it. But roughly this is the idea.
So maybe I also feel like something that just to me. So this, because of this asymmetric neutrino outflow, do you also expect to have some asymmetric secondary kick? That depends on the initial rotation.
So there are two things with the kick. I don't remember what I want to show. Okay, so first of all, usually you mean compared to a neutron, a core collapse supernova, or
naively I would expect, like, if you have like an asymmetric emission of any sort, like mass rejection or neutrino emission, you would also get some preferential kick.
Okay, so there is asymmetric emission, neutrino emission, but is axisymmetric because of rotation. So the mass outflow will be axisymmetric or spherically symmetric if you don't include any rotation. Usually to get when we mean very asymmetric, in our code, we basically solve from here to here, and the rotation, but it's basically axisymmetric. Because of rotation, you get mass outflow in the poles. So this is the same on the poles and on the north. So this will not create any kick. If you have the same mass going out in the north and in the south, I think this will not create. Then another question is that if you have so most of these objects will rotate in nature, and also when you have this fast rotation, you don't have the typical convection that we see in the star. So this also connects because there are two different kicks. If we talk about core collapse supernova, we have the kick that comes from asymmetric mass emission, but this comes because of asymmetries and instabilities that they develop during the core collapse phenomenon, because basically the mass accretion is very symmetric, but in 3 dimensions. And also, and this creates a very, the outflow is very, very different from this one. And then there's also the neutrino kick. I don't want to go into much details because I'm not an expert in that, but you also get a neutrino kick because of asymmetric neutrino emission. But with this kind of fast rotation, you don't get this kind of okay. So you get asymmetries in the poles and in the equator, but the asymmetries that you need for neutrino kick are very, very different. And yeah.
Thanks. Any final question from the speaker? If not, let's.
Thank you.
So.